Hi class, thanks for coming. We're at chapter 12, geologic time. Geologic time. The earth is, billions of years old. And the realization that the earth was billions of years old really was a big step in human history. What is meant by that is we didn't really have an understanding of the scale of geologic time. It goes back to the formation of the solar system and our place in the solar system, our place in the universe. That was really kind of vague until we realized how old the Earth was. So it changed our perception of time, changed our perception of the universe. It's important in geology to have that understanding of geologic time so that we can understand the formation of rocks, the importance and the story that is told by the fossil record, geologic structures. So in this image, here is a fault cutting through the landscape. We need to understand that that happened after the rocks were deposited. The evolution of a landscape also takes time, and understanding that the breadth of geologic time helps us understand the changes that landscapes can go through over time. We also can look at tectonic events now in the opening and closing of ocean basins and how many millions of years that takes. And then we have a clear understanding of that now. And just change in general, like things change over time. Metamorphic rocks metamorphose, sediments turn into sedimentary rocks. All of that takes lots of time. We put time on the geologic time scale. So here is the geologic time scale. We are in the Holocene, that is after the last ice age from the Pleistocene. The Pleistocene and the Holocene are part of the Quaternary, and the Quaternary is part of the Cenozoic. And the Cenozoic, Mesozoic, Paleozoic eras are all part of the Phanerozoic. So going back the other way, we are part of the Phanerozoic, here at the top of the time scale. Of the Phanerozoic, we are the youngest. We're in the Cenozoic. Of that, there's the Paleocene, Paleogene, Neogene, Quaternary, and we are in the top of the Quaternary over here in the Holocene, just after the last Pleistocene ice age. Geologic time hasn't, like we're saying, always been completely understood. There was a time when geologic time and like historic time, the time of humans, we tried to equate those over time. There was an archbishop who in 1654 went back through the Old Testament, the history of the Old Testament, looked at generation after generation, and came up with a birthday for the earth as October 23rd, 4004 BC. So that was really thought of as the age of the earth for a long time, till we realized there's a whole history of the earth that goes back billions of years, not thousands of years. So geologic time, Steno, Nicholas Steno, he was Danish, and just like a lot of the people who made big discoveries in early geology, he was a physician, and he looked at rocks in the Apennines. Apennines are mountain chain up the long part of Italy. And when he was looking at those rocks, he noticed in the rock record there were marine fossils. And how could that be? He figured out that, rightly so, that these marine fossils meant that at one time in that place there was an ocean. And those fossils were in the ocean, those organisms were in the ocean. They died, became a part of the sedimentary record that became sedimentary rocks that then was later, through tectonics, uplifted into the mountain chain. And all of those processes he knew was going to take something like millions of years. James Hutton, he was a farmer, not a physician. No, he was a farmer and a physician. And he was in Scotland, and he is who we call the father of modern geology. He came up with that principle of uniformitarianism, where the present is the key to the past. And he wrote that we find no vestige of beginning and no prospect of an end, looking at geologic time as going on forever backwards in time and on forever forwards in time. So he realized for the first one in the 1700s how much time there was to geologic time. So the present is the key to the past. It means that we can look at like these ripple marks that are on a lake or a river or the seafloor, maybe near the shoreline, and see that currents are moving the sand and making those ripples on the bed of whatever water it is. Then if we go to the rock record and we find ripples, then we can go back to the present and say, oh, I see how ripples form today. That must be how ripples formed in the past. So we're looking at geologic time going way back, and that we can find things that happen in the present and figure out how things happen in the past. That was James Hutton who figured out uniformitarianism. All right, so this chapter splits geologic time into two parts. We're going to look at relative ages and then exact or numerical ages. Relative ages means that we can determine the relationship between two events, two rock types, an event and a rock type. And that's just saying that one event or rock is older or younger than another one. It's just a relationship between the two, older and younger. The other kind of geologic time or age is numerical age. We can put an actual number on the age of an event or a rock, an occurrence in geologic history. So we'll look at how we can do geologic ages as well. This example shows where relative ages of our history of flight and space flight on the left, and then on the right, you can look it up and find the exact ages that these events happen. So they're pegged on a timeline. And that's pretty much how it works for geology. We can look at relative ages of the ages of rocks and events in geologic history, and then figure out through radiometric dating what the numerical age is. And it works.